Welcome everyone to the IEOR online seminar series. Today we have Professor Jamol Pender visiting us from Cornell University, the Operations Research and Information Engineering College. And Jamol had his PhD from Princeton University in 2013 and joined Cornell University in 2015. And Jamol has received a number of awards, including the NSF Career Award, the MIF Career Award, the Ford Foundation Fellowship, and several teaching and advising awards. And Jamol's research has been at the interplay of queuing, stochastic processes, simulation, and non-stationary dynamics. So without further ado, we'll have Jamol give today's seminar talk. Jamol.
All right, thank you guys so much for inviting me. I will sort of treat this as my class. If you have any questions, feel free to either say something or feel free to put it in the chat, and I'll try to answer those questions as they come. So I'm kind of delighted to talk a little bit today about a topic that I have been working on for the past maybe two years or so. And it's entitled Beyond Safety Driver Staffing a Teleoperations System for Autonomous Vehicles. I'd like to mention that this work is joint with two people. So the first person is Robert Hampshire, who's a professor at the University of Michigan. And the second person is Andrew Daw, who was my PhD student here at Cornell and has now moved off to the West Coast to join the West Coast folks and the son at USC at the Marshall Business School. And so just as somewhat of a precursor to how this work kind of got started, I've known Robert for quite a long time because we share the same PhD advisor. And I sent Andrew to Michigan, and I actually visited Michigan before this, but I observed that Michigan has like this really nice transportation research institute. And we actually talked with a few people about kind of autonomous vehicles while I was there. And so I sent Andrew there to start a project with Robert, and this is what resulted. So just as a outline of the talk, I'm going to give somewhat of a basic review of what teleoperation systems are. Hopefully you know what autonomous vehicles are. And then I'm going to introduce kind of a queuing model with batches that is used to think about how we should model kind of a teleoperations center. And then I will kind of develop a new theory for queues that have these large batch arrivals. And then we'll use some data from various companies such as Waymo to think about how we would actually staff these kind of centers in the future. And then I'll highlight kind of a couple future directions. One other thing I will talk also about is kind of how you might be able to use some of these models for some COVID research that we're doing as well. So this kind of research was motivated basically from this first accident with a self-driving car. So in 2018, the first person, Elaine Hertzberg, was actually killed by an autonomous vehicle, and it was a vehicle run by Uber. And why the name sort of Beyond Safety Drivers? Well, there was actually a safety driver in the vehicle at the time. And it turns out that the vehicle noticed that something was ahead about 6 seconds before she was impacted. And so there was a person kind of in the vehicle, and this person is called the safety driver. And they're supposed to sort of exactly protect from these kind of situations actually happening. Now, one thing that if you read the NTSB report that kind of discuss why the accident actually happened, what you notice is that Uber had turned off the sort of some of the safety features of the vehicle, so that the car would stop sort of starting and stopping. So there was some sort of glitches that was going on. And so they sort of temporarily had cut off the safety features, and it resulted in this sort of first accident. And so I entitled the talk Beyond Safety Drivers because um, we have to think about kind of moving beyond these types of people that we actually have in the vehicle. And for one reason, let me just give you that. If you look at the video, and it's kind of a horrible video of this first accident, what you notice is that the safety driver is actually looking at their phone. And I think it turned out that the person was looking at Hulu on their phone at the time. And so what kind of the technology of autonomous vehicles, it kind of actually lulled this safety driver to sleep. Well, you think, okay, well, everything's working fine, and it's supposed to be autonomous. I'm only here for kind of emergency kind of situations. Well, it turns out that the driver, or the safety driver, was not sort of paying attention, and this sort of definitely sort of, I don't want to say caused the accident, but it was sort of one reason why the accident certainly happened. And so we have to think about how we want to move beyond this. And so my talk is going to be somewhat of a methodology or a system that will help us kind of move beyond this in the future. Well, if you don't know much about autonomous vehicles, there's a lot of buzz going on about them. And basically, they're supposed to make kind of transit sort of safer, smarter, more sustainable than it currently is as of right now. And it also sort of alleviates the driver from actually doing any of the driving, which is an important thing for me if I want to go visit, my family in New York City. Well, that's 4 hours from Ithaca with no traffic. And so that 4 hours can sort of me driving can be replaced with 4 hours of me, reviewing referee reports. So so I actually could save a significant amount of time, and lots of people could sort of save a significant amount of time if they're not actually driving. So this is sort of projected that the global revenue from autonomous vehicles, if we ever get them working properly, could be a roughly 7 trillion. And this is not just for the person who wants to take, like me, who wants to take the trip to see their family. Uber, Lyft, many of these kind of taxi companies are really looking towards this autonomous vehicle technology, as they can basically get rid of the driver, and they can keep all the revenue for themselves. And so making this become a reality has become very important for many of these companies. So I like to say that when we think about kind of autonomous driving or autonomous vehicles, there's different levels where we would like to sort of see an autonomous vehicle operate. And right now we're sort of in this sort of level 4 kind of area. And our whole goal actually is get to this level 5. And most of the kind of test driving kind of situations, as you can imagine, have been in locations where things are very nice. So they test in, California, they test in Arizona, they don't test in Ithaca. So that is certainly an area that we certainly we would like to get there, where they are testing in Ithaca, especially after it snows. And so level 5 is really the level where the vehicle can basically operate under all conditions. So it should be able to operate when it starts snowing shortly in Ithaca, as well as it is on a sunny day. And so we haven't necessarily reached that level yet, but we're certainly in the sort of level 4 area right now. And we're hoping to sort of help the transition from level 4 to level 5. So much of the technology that I'm going to sort of be emphasizing today via teleoperations is sort of a way for us to move from level 4 to level 5 and also provide some sort of extra safety. And I should mention, actually, recently, as I think last week, there's been like a committee that's been tasked by the US government to think about how to set up these teleoperations. So they are becoming real. So a lot of companies, so Waymo and Uber are kind of leading the charge in teleoperation, have already sort of begun testing many of these vehicles outside. Many of them have these sort of LiDAR sensors that can sort of sense the environment. And I should mention that from an operations point of view, actually, these kind of sensors actually present a lot of interesting problems. So for one, like right now, it's sort of a sunny day in this picture. So the LiDAR kind of sensor can kind of sense, what is around, maybe try to sense whether there's a human around and how should it behave when there's a human around. But if I give you a scenario where now it's not sunny, but it's raining, well, the sensing technology actually works quite different. So it presents kind of a different environment than on a sunny day. And so the data that it's getting back and what it's sensing actually could be quite different. And so it presents kind of interesting problems to kind of infer like what's going on based on kind of the current environment. So there's lots of interesting problems, and I have a colleague actually in Buffalo who's kind of studying like, well, when it's raining, how well can we kind of detect people? For instance, when it's fog out, how well can we kind of detect people? And we have here kind of a very big issue today. Actually, was a big issue with fog. You can barely see a few feet in front of you. So kind of using an autonomous vehicle in the fog today probably is not the greatest thing to use. And so we haven't gotten to level 5 just yet. So there is a concern that we will never reach level 5. And one of the reasons is that if we would like to sort of demonstrate that autonomous vehicles are as good as humans, and we would also like to demonstrate that they do not sort of fail in a variety of situations, we'd actually need to sort of test them on a significant number of miles. And so this thing is sort of saying, okay, well, we need to test 8.8 billion miles to sort of demonstrate with 95% confidence that their failure rate is within 20% of our like whatever the true rate is. And so this was a report by the RAND Corporation. And they're basically suggesting that autonomous vehicles is really, really out in the future if we really want to accept these kind of rates of confidence. And so, like I said, our work is sort of helping to sort of bridge this gap of thinking about 400 years from now. Maybe I'll still be alive. I don't know. But 400 years with, maybe 10 years or 20 years, where we could sort of really see that autonomous vehicles kind of take over. Part of this sort of sentiment that we may not actually reach level 5 is due to the Waymo CEO sort of says that he doesn't believe that autonomous vehicles won't ever be able to drive in all conditions. And I would think that that's probably true. I could actually list a ton of conditions in Ithaca personally that I probably wouldn't think my autonomous vehicle would be able to drive in. But then I'm also comparing autonomous vehicles to something that I can't do either. So is that sort of a fair comparison to make? But certainly the Waymo CEO has a better sense of autonomous vehicles than I do. So one of the main issues is that sort of what's holding us back is that there are kind of these unknown unknowns. We kind of don't know what we don't know. And And when we enter these kind of specific cases of, we don't know what we don't know, it turns out that many of the autonomous vehicles do something called a disengagement. And so the vehicle actually suspends its autonomous operation. And so at that point, what does the vehicle actually do? Now, if there was an in-car safety driver, then that in-car safety driver could take over the vehicle once it disengages. But that doesn't necessarily, we don't necessarily want an in-car safety driver for every Uber that we're actually driving. That's basically like the situation we have now where people are actually driving the vehicles. And so we want to get to a situation where we actually have 0 people in the car who are like operating it. And so what can we do to sort of unlock this amazing potential for autonomous vehicles? And like I said, in-car safety drivers definitely offers a solution. But as we saw earlier, these in-car safety drivers can also have accidents because they're not paying attention. The technology is so good, it sort of lulls people to sleep. And this is why a lot of car companies don't necessarily say, okay, my car actually is a Nissan Rogue. It can pretty much operate by itself on the road, but they don't call it like autonomous vehicle mode anymore. They call it, vehicle assist. And it's really with the intention that, yeah, it can probably drive itself more or less on the highway. And I've done that. But at times they don't want you to sort of go to sleep because it's actually, driving itself on the highway. They still want you to kind of pay attention to the road because, there are situations, AKA the one we've seen earlier, where, something may happen and you're not paying attention. And so what do we kind of propose? Our proposed solution is to kind of build a call center for these autonomous vehicles. And here we have kind of a nice picture of a startup called Designated Driver. And the idea here is that, when a car kind of suspends its autonomous mode, the person here can take over the vehicle and help that vehicle either start the autonomous mode again or actually help the vehicle get to its eventual destination. And you can see that the person here who's driving the vehicle or sort of driving the vehicle autonomously or remotely has different sort of camera angles. They can see who's in the passenger side and they can see at all the different sort of angles of the car. And they can also see where their intended kind of destination is. Now, the most important one is sort of looking ahead, but you also want to be able to kind of see what's around you and also kind of what's behind you as well. So this kind of gives the remote driver here a full picture of kind of what's going on around the car. And so our goal is to kind of propose this sort of call center. And actually Nissan now is actually building a teleoperations center. And this is already being picked up across the country as a potential solution to help vehicles when they actually have these disengagements. So there's a variety of states now that are actually mandating teleoperations. So every autonomous vehicle that's being controlled in these states now has to have some kind of teleoperations system in the background that can help in some of these tough situations. So I want to be very clear here. I'm not saying that teleoperations will solve every single problem, but it will help us actually get to a place where we can think about kind of level 5 autonomous vehicles. So you're starting to see that in many of these states, these kind of safety drivers are still required. But I suspect that much of this map, it will first turn sort of navy blue, and then it will eventually turn orange. And basically the places where it's orange, it's either places, all the cars are basically made up here. And then there are places where, it's sunny and nice. So eventually, hopefully, we'll get to the States where it isn't sunny and nice. But that's sort of the plan. And like I said, the U.S. government actually is starting up kind of a teleoperations group of people who are starting to think about this at a national level. One other thing I'll mention is that when we think about teleoperations, and this is not necessarily the focus of this talk, but one has to think about whether this is somewhat governed by the states, or is it governed by kind of a federal level, or even is it sort of governed by the car manufacturers themselves? Um, so one thing I like to mention about kind of a comparison to the airline industry is that the airline industry does not compete. Oh, this is sort of a clause. They do not compete on safety. So all of the safety things in terms of the airline industry are really done at sort of a federal level. They're not done at the sort of individual airline kind of levels. And so maybe that's something that we have to consider when we think about kind of autonomous vehicles. Currently, as it stands, all of the safety things in terms of vehicles are really left at the car company kind of level. Now, there's sort of minimum standards. You got to put a seatbelt in the car and stuff like that. But a lot of those things are kind of left up to the car. And, you know, when you get your JD World and report on a particular vehicle, it does have kind of safety information. And all of those things are kind of, you know, car companies are competing with each other to be kind of the safest vehicle possible in the case you might get into an accident. And so we have to think a little bit differently when we think about autonomous vehicles in terms of safety. And this group that's being set up by the U.S. government is starting to think about some of these issues. So here are a few companies that are starting to think about kind of teleoperations. So I mentioned Nissan has started their own kind of teleoperations. Autopia is another startup, and so is Phantom Auto and Designated Driver are other startups that are also thinking about setting up their own kind of teleoperations systems as an alternative to our in-car safety drivers. I'd also mention that before we kind of get into a model on how to model some of these systems, there's also, there's calling on a remote driver to assist when the vehicle actually suspends its autonomous mode. But there's also helping the vehicle kind of choose the right path as well. And so this startup Autopia actually offers something called advanced teleoperation, where basically you kind of have humans in the background who are given kind of certain paths. And effectively, their goal is to kind of drive the vehicle in the correct path. And you have multiple people kind of doing the same exercise, and you kind of take an average of their results. So you kind of take, you sort of crowdsource their results, and that's something that the car can actually learn and do on its own as well. And so one thing that they do is like, okay, I want to operate the car in a snowy environment. What should the car kind of be doing on a path where you can't actually see the lane markers anymore? And so you actually have human people who are actually driving the car kind of in those situations, and the machine, or the actual sensors and computers in the car can actually learn from the human kind of behavior. And so they call this human in the loop. And this is something that a lot of car companies are considering right now, where you have these kind of people who are helping the artificial intelligence actually learn as they go. This is Nissan's kind of setup where they're doing kind of seamless autonomous mobility, but this guy is actually kind of drawing out a path for the car as well. And so in this case, the system can actually learn from the humans, and you can present it with many different scenarios, and hopefully the humans actually get it right. And like I said, the sort of AI can learn from the human behavior. So I'm happy to take any questions right now before we kind of get into the modeling part of the talk. If there are any questions, I'm happy to take them now before we move on. So there's a question about has a lot of this ground been covered in drone support? Can you elaborate on that question? You can talk if you like. Yeah, I think I think there's a lot of areas where I think some of this technology certainly can be used. I now actually, maybe about a year ago, I had some students kind of do a project on thinking about kind of drones and queuing theory, which is um, somewhat of an interesting topic. And mainly because actually we wanted to uh, one of the tough things about living in Ithaca is that you kind of have to go up hills, and going up hills when it's sort of snowy is not so great for delivery options. So we've been thinking about kind of delivering things via drones, um, and well, they sort of take time. And we've also been sort of thinking about this is, should you have kind of a human um, operating the drone, or can the drone kind of work on its own? So there are kind of interesting set of connections to this that I think probably could be applied to kind of situations where you have drones. Um, so just to get a sense of um, what we're doing in this particular problem. So what's happening here is that you have your car. Perhaps, let's not say we're in sort of a disengagement mode, but let's say the car is actually perhaps going to see something above that it doesn't like. So what it could do is actually send something back to the command center saying, hey, I'm in an environment in which I think I'm a little fuzzy on. And on this command center, they will send this to multiple different people, and these multiple different people will sort of, in some sense, draw a path. So this is kind of what we envision kind of path choice to be. They will draw a path for the vehicle, and the vehicle perhaps has slowed down a bit. It doesn't know what it should do, and so we'll draw a path, and then the vehicle can kind of continue on. Now, ideally, the vehicle should still be kind of going in some sense. Maybe it's going at a slower rate because it's uncertain. It's seen some behavior up here. These people have now actually sort of drawn the correct path in which they think the car should go. And all that information somehow is transferred back to the car. So we're hoping in a world where we have 5G, this can be done actually within 2 to 3 seconds. You may kid me, you may think I'm kidding on that, but actually there's a pretty good literature on how to do kind of just-in-time crowdsourcing, and they do it in about 3.5 seconds. So this is kind of what we envision. All of these different people kind of have the same task. They kind of want to be able to draw the path for the car. But as you can see, there's multiple people here. And so what we're going to do is relate this to kind of how many people, every time a car gets in a scenario, well, we're asking people, multiple people, to come and assist. And we're kind of using their crowdsourced knowledge to help operate the vehicle in the future. So this goes back to our sort of fundamental question of how many people does it actually take to run one of these kind of teleoperation centers? So this question I'm going to reframe as, how does one staff a queuing system with a large batch of arrivals? And we're not talking about like 5 here. We may be talking about 10, we may be talking about 100 people. And so we're really thinking about, queuing systems where you kind of have this large batch of arrivals. There's been kind of somewhat of a large literature for many years. It also goes under the name bulk kind of queues on queues with batch arrivals. Um, but many of the sort of literature kind of either thinks about bounded batch sizes, or they kind of make assumptions where the batch size is not large. And so one of the interesting things I'm going to do here is actually devise kind of a new kind of scaling regime where we this time use the batch size itself and scale the queue with the batch size. And we're going to scale the number of servers also with the same batch size. Um, so this is what we call a batch scaling. Many people who've worked in queuing theory have studied maybe, I'll say 3 types of scalings. One of them is your sort of conventional heavy traffic scaling, where you kind of scale lambda and you also scale the service rate. There's also the half and width scaling, where you're going to scale the arrival rate and you're also going to scale the number of servers. And then there's also this sort of non-degenerate slowdown regime where you can actually scale not only the arrival rate and the service rate at different proportions of n, but you'll also scale the number of servers by n as well. And you get this sort of interesting regime that sort of combines the half and width regime with the sort of conventional heavy traffic regime. So those are kind of the basic scaling regimes that people have studied in the literature. And so one thing we wanted to do was study a different scaling where this time the batch size is growing with n, and we're going to keep lambda sort of fixed, which is the arrival rate, and we're going to scale the number of servers. And you'll see why this is actually a very different limit than what people are generally used to. And like I said, we call this our batch scaling. So what we're going to do, we're going to model this teleoperation system as follows. You're going to have a general kind of arrival process, and you're going to have a general kind of batch sort of distribution. But this batch distribution is going to depend on generally what the batch size is. So if you think of the batch distribution being deterministic, well, that means that each time a disengagement occurs from an autonomous vehicle, I'm going to get n people that are going to do my just-in-time crowdsourcing. And those n people are going to work. And then eventually those people leave the queue and they sort of enter back in the system. So we're going to assume that the service times of each of those servers that are dealing with the who are sort of drawing these paths to the vehicles, these are also sort of generally distributed. They're just IID. You can think of this as a renewal process. And then we have C times N servers. So this is kind of the setup. This is kind of a multi-server queue with batches. But the key insight here is that we're going to scale this number N, which is going to be our sort of mean batch size, is going to be order N, and we're going to scale the number of servers. So hopefully that is clear. And just to give some motivation, we think about the disengagements here happening. This is going to be our arrival process. So this, like I said, the jobs will arrive at the disengagement time. So the vehicles will suspend their autonomous mode, and then that will trigger sort of more jobs, and each one of them will have some batch size. And then, each one of those jobs will be worked on for some time with some service rate. So this means we're going to have these batches occur. And ideally, there should be very fast service. So, you want the person to kind of draw the right path in the right amount of time. And that information eventually is fed back to the vehicle. And like I said, safety kind of calls for large batches. So we want large batches because we want more people to kind of put in their input. While at the same time, we're going to think about the more people that we call on to put on their input is going to affect the performance of this queue. And therefore, we also need a large number of remote operators as well. And so the whole goal here is to figure out what is this number of remote operators we would need based on the information of our disengagement. So we've now kind of set up this sort of ideal model that will kind of was motivated by our teleoperation system. And it's a queuing model, and we're going to do some analysis to figure out how can we gain some insight about this particular model. As it stands, this model is basically intractable to get anything out of it, especially when you kind of have these general distributions. And so one thing that we often do in kind of queuing and stochastic processes is we leverage kind of either the law of large numbers or we leverage the central limit theorem. And here today, we're going to leverage kind of the law of large numbers, but you'll see that the limit that we get out actually is not deterministic as it usually is. It's actually still a random quantity. So one thing before we get to analyzing this model, which is the multi-server queue with sort of large batches, I'd like to analyze this situation where we have a infinite server queue. And this is very common in the literature. We like to analyze the infinite server queue because it basically gives us a bound on how our multi-server queue system would work. So it gives us kind of a nice lower bound on the multi-server queue. And it also gives us insight on, well, what's the mean behavior of this system, or what's the variance of this system? And this system is always kind of generally much easier to study than its multi-server queue counterpart. So we'll begin there, and this will actually give us insights on how to solve the multi-server queue as well. So let's try to understand what's going on in this infinite server queue setting. So we start with the queue length, and how can the queue length, and I'm indexing it by n, which is going to be our batch scaling. So we index this thing by n. So what's the number of people in the queue at time t? Well, it's the number of people that have arrived. And each time there's an arrival, well, this triggers a number of batch, a batch size. And so a number of people are going to, a number of requests are going to arrive from that batch size. And I'm going to ask, well, if that person I arrived at time I, so this is the arrival time of that batch, plus their service time. So it's the service time of person I, or I should say of batch I, and of, within the batch, we have a subscript of J, which is counting the Jth person of batch I. So basically, there's an indicator that counts whether this person is still in the queue, whether their arrival time plus the service time is greater than T or not. So if it's greater than T, they're still around. So you count them as a 1. If it's not greater than T, then this becomes a 0 and they've left the queue. So this is an explicit kind of representation of the queue length using these indicators with a sum of our arrival process and each batch size that subsequents each arrival. So that's the queue length. Now, what we can do is scale this queue length down by n. So all I did was just multiply both sides by 1 over n. And what I'd like to do is do a really nice trick that everyone has learned, multiply by 1. So what I did here is I multiply by bi of n in the numerator, and then I'm also dividing by bi of n. And by the way, bi of n cannot be 0. So otherwise it shouldn't count as a batch or an arrival. So in this particular case, I'm just multiplying by 1, but you'll see here that I'm trying to get this thing to perhaps look like a law of large numbers. So it's kind of 1 over the number times a sum here of this number. And so I'm going to group this together. And so if I take this particular limit, well, what happens to this quantity here? If I box this quantity here, well, this quantity here begins to look like this quantity here. So G bar is the distribution of each of the service times. And why can I do that? Well, if I take a large number of these indicator functions, well, it's approximating the actual tail CDF of the distribution of these service times. So we get convergence to that tail CDF. Well, now if I look at this, this actually represents the number in the batches, but if I rescale it, one can think of this as a mark. So when you think about shot noise processes, each shot noise can jump up by the mark size, which we name M sub I. And so it turns out that this queue length process in the infinite server case converges to something called a shot noise process. And shot noise has been studied since like maybe the 1900s around. I think there's a guy named Shotsky actually who has a paper that came out in physics where they're looking at these sort of jumps in many kind of physical processes. And so this shot noise actually results in this limit. And so hopefully you can get some intuition. Okay, this piece here converges to our sort of tail CDF. And then this piece here converges to whatever jump size we get out in our system. And so shot noise has been studied for a very long time. And so it turns out for the infinite server setting, instead of looking at the queue length directly where we don't really know much, we can kind of just look directly at kind of shot noise processes and study those. And there's a lot of literature on kind of shot noise processes. One thing I'll mention is that this limit also is random. Now, we did not get rid of the arrival process. So in kind of basic queuing results, more often than not, you're scaling some arrival rate. So this thing kind of disappears and becomes like just a constant. But in this case, we're actually still getting a random process out when we take this limit. So I want people to be aware of that. So here's like an example of this. So I've have my scaled kind of queue length in blue, and I actually just plotted the subsequent shot noise process that results out. And for large N, I think in this case, N was like 100. You actually see that the performance of the queue length process follows this actual shot noise process. So what happens in shot noise is that every time there's an arrival, there's a jump of some size, and then you kind of decay according to that distribution G bar down towards 0. And then there's an arrival that occurs, it shoots it up, it decays again, arrival occurs, it shoots up, decays, etc. So that's kind of what we view as the shot noise. So in our particular paper, we kind of prove this for the infinite server setting, that this queue kind of converges to this nice shot noise process. So that is the beginning. And now we need to sort of think about kind of how we can actually use this understanding of the infinite server to understand the multi-server setting. So we'll do that. So the main idea here is that we're going to use the infinite server in our multi-server kind of queuing system. So what is this saying? So I want to capture the multi-server queue dynamics also with indicator functions. I love indicator functions. So you can write the whole dynamics of the multi-server queue in terms of indicator functions, but I write it in a way such that this first part here is identical to the infinite server queue part. And what's left over is a piece that measures the people who need to wait around. So if you don't need to wait around, you're identical to an infinite server. If you do need to wait around, you're kind of like an infinite server, but plus this waiting time. So the whole kind of key ingredient here is to understand what this piece is, because we know this piece quite well. So just to think about this a little bit differently, you can think about this first part not only as an infinite server, but as a part where jobs start immediately. So it has that infinite server flavor. And this part are all the jobs that need to wait. So you can think of, like I said, immediate and then things that have to wait. So one of the important ingredients in our results is we use kind of a result from Josh Reed's kind of seminal paper on multi-server queues. What he kind of showed was that you can take the queue length minus the number of servers and integrate against the service distribution. And that actually is a representation. So he didn't have batch sizes, actually. But you can represent this as a sum of the difference of their sort of tail CDFs. And so we sort of generalize this result to queues with batches, and you get this nice extra kind of sum in the middle here. So this result actually will be quite useful, because you can think of this integral as the people who are waiting around. So what's going to happen is follows. We're going to pretend every single person that arrives is going to be in our infinite server queue. So if I can go back. So if every person that arrives is in our infinite server queue, then as soon as you walk in, you're going to start service, even if you have to wait, actually. And so what we need to compensate for, and this is actually where you get compensated, is that for the people who actually need to wait, so this is the number of people minus the number of servers. So you take all the people who are waiting, you're going to integrate them against the service distribution, and you're going to add that sort of, integral up. And that is equal to the amount of time that that person has kind of waited in service. So if you think about your service time, if you started, even though you have to wait, if you start in the system and I pretend you already started, I have to compensate your process sort of getting done by a server by something else. And this is that something else. And so we're actually characterizing the infinite server part that's being subtracted away if you have to actually wait for service. So that's actually what this piece actually is. So here, let's go back to our decomposition. So our decomposition goes back to this infinite server part, jobs that don't have to wait, and then jobs that do have to wait. And what I'm going to do is I'm going to subtract off this piece and this piece. So that goes, I'm adding this piece and I'm subtracting off this piece. And in that previous lemma, I showed that that was 0. So I'm basically adding 0 to the equation. And what I'd like to do now is sort of match up interesting parts. So now I have the same infinite server part. I have this piece that came from here. And now what I'm doing is I'm subtracting the indicators that come from here. So this indicator comes from here. And then there's an indicator that comes from here as well. And I'm subtracting off the subsequent parts. Like if you thought of these as sort of martingales, these parts are actually going to disappear. So I have my nice decomposition, and I have it in an infinite server part. I have a part that I'm sort of replacing back after considering every arrival starts immediately. So I'm compensating for starting immediately on all of the arrivals. And I have two pieces, one an indicator function and one effectively the expectation of the indicator function together. And what we're going to do is we're going to take limits, and this part and this part are going to disappear. And we're going to be left with some pieces here. So now I scale everything by 1 over n. And like before, this part should go to our shot noise. This part will go to some piece that we'll talk about. And these two parts actually should disappear. And so the first part goes, like I said, goes to shot noise. This is our infinite server part. So this goes to shot noise. This part goes to 0. Basically, it's an infinite server. And I know that this converges to the infinite server shot noise, but this exactly is the infinite server shot noise. And I'm subtracting off the same component. So this piece goes to 0. And for the same reasoning, you can use martingale differences to show that this piece also goes to 0 as well. And last but not least, we're left with this interesting piece here, which actually converts this not into a shot noise, but it turns it into what we call a storage process. And so what we can show is that Q length distribution, as I send the batch size off to infinity, converges to something called a threshold storage process. And it's generalized because we're actually using kind of general distributions. And these, unfortunately, like the regular shot noise, these have not been studied as much. And so we've been doing a lot of work and trying to understand these processes in a little bit more detail. So the main result here is that our Q length actually converges to this storage process. And you may think, okay, well, you show convergence to something that's even more complicated and you don't know anything about it. But actually, from a simulation point of view, this storage process is actually much easier to simulate. And it's much quicker actually to kind of solve for various C values for performance. And why is that? Well, you don't actually have to wait for things to sort of disappear as you do in the Q length. You actually just increase, and this thing is deterministic in between the arrival epochs. So it kind of behaves like a differential equation in between the arrival epochs. So it's much easier actually to kind of simulate because what you're doing is kind of like a forward Euler in between the arrival epochs. So you don't actually have to keep track of anything, which makes that actually much easier for doing kind of a simulated kind of staffing kind of analysis. So here's an example that I probably will skip on behalf of time. But anyway, the idea here is that we're going to pretend that the service distribution is exponential. And the whole goal of this is to show, okay, if I plug in this exponential distribution and I actually take the time derivative, well, what do I get out in the end? I get out actually mu times the storage process minimum C. So you actually get this nice kind of function in between arrival epochs. So like I said, you actually have a differential equation that describes the behavior of this storage process in between the arrival processes. And basically it decays according to this function. So the exponential case is very nice because you get a very nice differential equation that you can use to model between the arrival epochs. So what we can do is think about, okay, how does this Q behave with large batches? So in this case, this is the Q length divided by N. And in this case, N is equal to 5. If we scale this up to 50, you can start to see that it actually is starting to look more continuous between those jumps. It's sort of decaying down according to that differential equation. And if I go to 500, you can barely tell that it's not a continuous process. So you can see that we have this nice convergence to this generalized storage process. So now that we sort of prove this result, how does this help us kind of staff our queuing system that we were sort of motivated by earlier on in our teleoperations? So here's kind of a summary of what we've done. We have this queuing system. It's modeled by this multi-server queue. And this is the number that we wanted to see, how many people are going to motivate or staff our teleoperation system. So what we came up with is, well, we have a storage process. It sort of looks even more complicated now. We have a storage process, and our goal is to figure out what level C actually gets us the performance that we want. And like I said, I will mention again that this process, especially in the exponential setting, and even in the non-exponential setting, it's not that hard because it's just an integral, is actually much easier to sort of simulate. And one can use kind of a iterative staffing kind of approach on this generalized storage process to actually figure out the level C that you would want to get. And it's much faster than simulating actually the original queuing system. So this can actually be used, I think, in a very practical setting where kind of the iterative staffing could not really, because you actually have to simulate everything and actually understand kind of what's going on even between the arrival epochs. So what we can do is also leverage our storage process. So remember, our queue length is in the multi-server queue. We basically want to understand when does this exceed our number of servers. So this means that people have to wait in order for a remote operator to help them out when a vehicle disengages. If I divide both sides by n, now I'm asking, well, this scale queue length, what's the probability it's greater than C? And for large batch sizes, as we intend to have, this basically looks like what's the probability our storage process exceeds the level C. And so we can use this actually to kind of calculate various results about our original queue length process. And there's some interesting results about, especially in the exponential setting, you can actually explicitly calculate this probability in terms of a simple integral. And so right now we're actually working on how to extend this outside of the exponential setting. And so you can actually calculate these exceedance probabilities very quickly without doing any simulation at all. So here's kind of the goal. We want to set our exceedance probability to some level epsilon. What you could do in terms of simulation is basically set an exceedance level, do a bunch of simulations, let's say 10,000 of them, see what the probability is. And if it's below, then you can possibly decrease. If it's below epsilon, you can possibly decrease your level C, run it again and see if it's closer to epsilon. If it's above epsilon, then you decrease you increase your staffing level C, and then you run it again until you kind of get closer to epsilon. And that's kind of the goal if you were to do kind of a simulated approach to figuring out the staffing level with this storage process. So what do these results tell us? So we took some data from various resources. So we took the actual disengagements from Waymo and GM Cruise. They actually are required to give disengagement reports about when vehicles disengage. So we took that data. We took some data from the National Household Travel Survey. And we took also some data from New York City. There's a popular kind of taxi data set that we also took there. And we sort of compared looking at the fleet size we staff the system as the fleet size grows. So in this particular case, we're looking, so on this axis, we have the number of sort of remote operators needed. And here, N is basically that batch size. So we took them kind of deterministically. And this would be an in-car safety driver. So it's a one-to-one pairing for each vehicle that's needed. And as you can see, we're sort of growing much slowly than the one-to-one particular pairing. So how should one think about this, even with large batch sizes, so 100 people? Well, what we're doing is that we don't necessarily need the sort of teleoperation system that often. We just need it whenever a car disengages. And so we're kind of trading off the disengagement rate, hoping that the disengagement rate is low relative to the number of people that we need when a disengagement actually occurs. And so we're trading off that here, instead of having a 1-to-1 pairing at all times, we have a n-to-1 pairing when needed. And we think the probability of being when needed is very low. And so that's why we can actually get a decent kind of trade-off here, is because the probability that a disengagement actually happens is actually quite low in reality. And that actually is pretty decent from the Waymo data set. So the average US driver kind of drives about 13,000, 14,000 miles a year. And so it turns out that Waymo disengages, their vehicle kind of disengages like every 12,000 miles. And so that's roughly one disengagement a year, as opposed to, you drive your car probably way more times than that. And so that's kind of the trade-off that we're making here. So one other observation is that this staffing is sort of sublinear in the number of vehicles, which is a very nice kind of observation. What's interesting also is that the staffing is exactly linear in the batch size. So if I go from 250 to 500, it is exactly double. So this is an effect of the batch size. If I need 2 times as more people, well, I'm going to need is 2 times as many more operators. And so it doesn't have a sublinear effect in the batch size. So we actually sort of projected how many operators we would actually need in various metropolitan kind of areas based on kind of the number of miles driven and how many disengagements they would have. And so this seemed to be kind of the size of how many operators per batch size we would need. And this was also how often those teleoperations people were actually used in practice. So one of the interesting things is that since this is like a very stressful job, these people actually need a break after they sort of perform the duty. So we actually probably need a lot more operators than sort of what the queuing model would suggest. So one thing we're looking at now is thinking about, well, if we build in kind of a random time after each server is finished, what is the utilization of the system at those points. I will mention that, so we looked at kind of this teleoperation system for autonomous vehicles. We tried to figure out how many people would fit in this particular system, how many would we need. There's a lot of things I think that were hopefully you learned today. You learned how to use queuing systems or queuing theory to model this teleoperation system. One thing I discussed was that batch scaling, which is completely new to the queuing literature. And we certainly believe that this kind of teleoperation systems can certainly help autonomous vehicles move from level 4 to level 5. I like to also say that this model actually is very relevant for how we think about COVID-19. So at least on Cornell's campus, we have we had in-person classes this semester. And I think we did a great job, and operations research, I think, is now starting to get the credit that it deserves for having impact on at least Cornell's campus. And I'd like to think about, so how do these large batches of arrivals affect or sort of model COVID? So we actually have a hotel on campus called the Statler. And this hotel actually housed all of the students who contracted COVID during the semester. But what happened is that basically students would arrive in batches. And so our hotel has, maybe 100 or so, 200 rooms. And so this kind of theory even worked pretty well in the context of small batches, such as size 10. But when we had kind of small to medium kind of COVID outbreaks, they were on the order of 30 to 40 students. And so this kind of work also can be used to think about, how large of a hotel do we need to have in order to make sure that we don't exceed sort of capacity for students on campus. So there's a lot of interesting work that's being done, I think, now on these batches of arrivals, and also thinking about how we collect data in general about COVID. You see like large cases per day, and then batches of people are going into hospitals. So I think some of this analysis can certainly be used in that context. And I've also seen some interesting work on how people are using, well, they haven't been using batch arrivals, but they should be using batch arrivals for thinking about how people are using up PPE during COVID. So you probably, as a doctor, you're probably not using one set of gloves. You're probably using multiple sets of gloves every time you see a patient. And so thinking about, batches of gloves being used as you kind of see more and more patients, thinking about how we use PPE is another kind of application of this particular model. I'll kind of leave with this note that there's lots of interesting things to study. I'd like for you guys to think about one thing. If we got autonomous vehicles, like done 100% perfectly, we should also think about how this would affect other industries as well. And I'll give you one example. In the healthcare space, if autonomous vehicles were perfect at driving, we no longer effectively have donors for different organs that we currently do have now because people get into accidents. And so this actually would affect the donor pool. Now, I don't want anybody to die in a car accident, but we do have to think about the impacts of autonomous vehicles on other parts of society. And so I'll leave you with that, and I'm happy to take any questions.
So Jamol, the sublinear rate that you established and showed in the plot, what exactly rate is that?
So this is sublinear in the number of vehicles. So as I think about the what is it, the number of sort of disengagements. So you can think about the number of disengagements that happen. How many operators do I actually need to satisfy that particular demand? So that is what's sort of sublinear here.
Yeah. So I mean, the rate, is this like a square root type of rate, or what's the result that you established?
We think it is somewhat square rootish.
Okay.
We haven't necessarily established precisely what it is. From data, it seems like a square root rate, but we haven't precisely kind of characterized what exactly it is.
I see. So do you think this is an interesting theoretical question to pursue, or it's more?
No, it definitely is. We just haven't done it yet.
Okay, got it. But you believe that it's most likely a square root?
Yeah. But yeah, like I said, the linear part is actually where you actually increase the batch size, and that actually just jumps up linearly. So so which is a little different than our sort of traditional kind of heavy traffic results. In fact, the referees asked about this question, and it made us think about it a bit. But yeah. we still haven't sort of got the precise result about the sublinear growth.
Right. Yeah, that's my question. Thank you.
Thank you for a very nice talk. I had a question that, a technical question that sort of became moot. It's a very nice analysis, but when you were showing about the infinite server queues and then,
I can go back.
well, yeah, but when the infinite server queues and then when you modified it to allow the finite server queues and you had the two pieces, yeah, so there. And I was thinking, well, yeah, what about those WIJs? You know, that would be the hard part to figure out, you know, how do they behave, whatever. But then you had this elegant analysis that sort of made them magically disappear because of these lemmas.
Yeah. So once again, this part is
Right.
this captures. So what this is capturing is if you're left around waiting, I'm integrating you against the service time. So I'm basically counting you as like I'm taking away whatever service you're getting.
Right.
So if I take away the the infinite server is pretending I am being served, and this is calculating me being or it basically is taking away that part.
Right, right.
And so it's only true until like I'm actually gone out the system.
Right.
So that's kind of the insight here of how to capture that piece. So you basically want to put the piece back that you're counting away. And so this accounts for the people who are kind of waiting around.
Right, right. Yeah. So it's very nice, very elegant.
Yeah, I'm telling you, like ever since in grad school, I became obsessed about indicator functions. They really actually, at least in queuing, I think they make like your life so much simpler.
That's right. Well, there's a few of my students here listening to you in my stochastic processes course, and yeah, they know I'm very fond of indicators also.
So I've actually been thinking about just redoing probability, just like forget probability, like P, and just do expectation of indicators. It's there's actually a book, I think it's called Probability via Expectation.
Yeah,
And,
yeah, which is one way to do it.
Yeah, I think it's way more illuminating.
Yeah.
So it's so yeah, this really is the key piece to this work. And I'll take some credit because we established this in the batch setting, but a lot of the credit does go to Josh for I don't think he understood it that way, but I do think a lot of credit certainly should go to Josh for his result here. But understanding what piece needs to come back is the critical point there.
Very nice.
There's a question in the chat. So what about the heterogeneity of expertise in members of the crowdsourcing team? And so, yeah, that is something that we've considered. Another question that I often get also is, I'll show you. Heterogeneity is okay. We can capture that actually through the randomness through the service times. But another question that we also get more often is like if everyone's sort of drawing the same path, then their service time actually may be dependent upon one another. So you would expect that they're going to draw something similar. And it turns out you get different processes if you actually include dependence. So you get these kind of shot noise-esque or storage processes. And it really depends on the dependence. This is why, I try to emphasize in all my probability classes, like correlation means nothing, but it really is about kind of what dependence you have. we have some kind of preliminary results on like certain types of dependence. You get this kind of storage process in the end. But the dependence actually does change the system, or the process you get out in the end, quite radically. So dependence really matters on how you capture that service time dependence. And so you could also kind of group people together as well. It's another kind of methodology. So you think I have some slow people, I have some fast people, I have some medium people, and thinking about grouping them together. This, I didn't mention this, but one of the things that we're interested in doing now at Michigan is doing kind of real studies with people. So how they actually drive the vehicles. So you could think of these as like small tasks. So suppose I have a vehicle and I want to actually get it onto the road. So how long does it take a real driver to pull out of their driveway and get on the road versus someone who's doing it via remotely? So generally you would think the remote operation actually would be longer, which is true, but how much longer? And so thinking about the kind of important tasks that would arrive in kind of teleoperations, you know, what is the time needed to spend in terms of doing those tasks? Because that actually goes into these kind of service times if people are kind of remotely controlling the vehicle. But also another important ingredient there is also training. So how long does it take to kind of train a person to remotely drive a vehicle? So that's also an interesting question. One thing I didn't mention here also is that beyond kind of the sort of path choice and the way that I sort of drew the figures of kind of the teleoperation system, one can think about in the trucking space, you actually have multiple trucks kind of going on a highway together. They call them platoons. And perhaps if one of those trucks disengages on the road, all of those trucks actually will disengage. And so you actually will have kind of batches on batches. And so so we've been thinking about that as well as another kind of possible scenario, where you have multiple kind of trucks. And so how people really envision that, you know, we will make kind of a highway for trucks. Trucks can kind of go on the highway autonomously, but once they reach kind of a city kind of area, then they will have kind of an explicit, you know, remote operator that might remote them through the city. Or once it suspends its autonomous mode, you could actually have a real trucking person kind of drive it to its final destination. And that actually would eliminate a lot of the accidents that we see on the highway with truckers, mainly because they're sleep deprived. And this will actually keep them in their communities. They don't have to necessarily drive kind of large distances. So we're looking at lots of different things that I think are certainly apply in the real world.
Thank you very much, Jamol, for this really inspiring talk. And yeah, it's again our great pleasure to have you here visiting us today.
Yeah.
Yeah.
Thank you guys, and enjoy the sunny California. We had some snow here the other day, and I was just thinking I got to get out to California at some point.
Yeah, sure. Yeah, and Jamal, by the way, you know, so maybe we'll stop the recording now.